Okay, welcome to my YouTube channel. Dear students, today we will discuss the magnetic properties of materials. Magnetic properties of materials. So, the magnetic properties of the materials here, first of all, there is one thing that weak magnetic field, weak magnetic effects can be seen in case of solids, liquids, as well as gaseous materials. So, but the strong magnetic effects will be seen only in case of solids. So solids have strong magnetic effects because of the particular geometrical shape. So first of all, we will discuss how this magnetic effects within the material comes from. So here you see the cause of magnetic field, cause of magnetic effects in materials will be due to the presence of atomic magnetic dipole moments. So there is presence of atomic magnetic dipoles in every material. So due to these atomic magnetic dipoles, there is a magnetic effect within the material, so that we can write, so this atomic magnetic dipole moments will be due to the three types of motions, like orbital motion of electrons. So you know the electron is orbiting around the positively charged nucleus in a circular orbit, will give rise to the magnetic moment and participates in atomic magnetic dipole moments of the material. The second is the supine motion of electrons. And you know the electron supines about its own axis, so this will also give rise to the magnetic moment within the material. And the third one is the nuclear supine. So these three types of motions are responsible for creating the atomic magnetic moments, and due to these atomic magnetic moments, there is a magnetic effect will be seen within the material. So first of all, you see the orbital motion of electron. Orbital motion of electron, you see, if it is a positively charged nucleus, the electron is moving around this nucleus in this orbit. For example, if the direction of electron in this orbit here, it is in this direction, here it will be in this direction. So the direction at these 2 pointers will be seen, it will be opposite. Here it is in this direction, here it is in this direction. So the direction of it, yani here you see this is like a current carrying current loop. This is equivalent to a current loop. Here you see if this is the direction here at this point. So if this tip represents the direction, and by right hand rule we can find the direction of the magnetic field. If this thumb represents the direction of the electron in a circular orbit, here these curl of these fingers will represent the direction of the magnetic field here. Here the direction of the magnetic field will be like this. Here it will be this. So the direction at these 2 pointers on this circular loop will be opposite, and here it will become, one is become north pole and second is it is like a tiny magnet having 2 poles. That is, here it is north pole, here it is south pole. So there is a magnetic moment associated with it. It can be represented as this arrow. So this is the magnetic moment and can be and representation is the mu. So here in this case we will represent, we will write a simple relation. This is a classical model basically. Here you write the velocity, linear velocity will be related to the angular velocity as r omega. R is the radius of the orbit. And if we divide both sides by 2 pi, here it is v divided by 2 pi will be equal to r omega upon 2 pi. So we can write it as v upon 2 pi will be equal to r, and here omega upon 2 pi will be equal to 1 upon t, that is a time period. Omega upon 2 pi will be equal to time period. So we can write here r upon t. So it will become v upon 2 pi r will be equal to 1 upon t. So this is the relation for inverse of time period. Therefore, the magnetic moment associated with this orbital motion of electron can be represented by mathematically, that is mu will be equal to current into area. Here magnetic moment will be equal to current. Here current is by definition will be equal to charge divided by time. Here we can write charge of electron, that is minus E upon time period multiplied by area of this loop, that is pi r square. So magnetic moment will be equal to, here it is minus E upon T multiplied by, here we can substitute the value of 1 by T will be V upon 2 pi R, and multiplied by pi r square. Pi and pi goes, here r and square goes, there remains mu will be equal to minus E VR upon 2. So if you multiple and divide by m, that is the mass of the electron, here it is m. So here in this case m VR will be equal to L. That is the angular momentum, and it is a quantum mechanical quantity and it is a measurable quantity. So this any linear operator L will be substituted here. So mu will be equal to minus E upon twice m into L. It is a vector. Here this is also a vector quantity. So this is the relation between mu and L. Mu is the magnetic moment associated with the orbital motion of electron, and E upon 2m is a constant. Charge of electron, 2, and mass of electron. So this is all constant. So the magnetic moment only depends upon the angular momentum. That is the angular momentum vector. Here you see the direction of the angular momentum vector is here along this direction, that is here it is L. So the magnetic moment will be opposite because of the negative sign here. You see magnetic moment will be opposite to the direction of the orbital angular momentum. So that means we remember here that whenever there is orbital angular momentum, so there is a magnetic moment associated with it. But in case of ground state and electrons, ground state electron like hydrogen atom, the electron lies in S state. That is because the orbitals are described as S, P, D, F, that is electronic configuration. Here you see here for S, the azimuthal quantum number, that is L equal to 0 for S, L equal to 1 for P, L equal to 2 for D, L equal to 3 for F orbit. So for S orbit, L is equal to 0, that is azimuthal quantum number. So it is related to the orbital angular momentum as L is equal to under root of L into L plus 1 into H cross. And this is quantized actually. So orbital angular momentum is quantized and is related to the azimuthal quantum number as this. So if L is equal to 0, then orbital angular momentum will be equal to 0. So there is no magnetic moment associated with this, because orbital angular momentum becomes 0, but yet there is angular momentum as L is also equal to 0, because therefore there is a magnetic moment associated with an electron even the orbital angular momentum is 0, that is the supinning motion of electron. This supin was confirmed by an experiment called Sutton-Gerlach's experiment. So here I am interested to tell you something about this experiment, and here you see in this experiment they take an ohm which is coated inside with silver coating is there, and which is at a temperature of very high temperature, that is 1000 degree. So at this high temperature, silver is in vaporized state. So here there is small hole, the silver atoms can pass through this, that is the silver beam of atoms, and in front of the silver beam there are two slits will be placed here, and these slits will collimate the silver beam and after that there is a magnetic field placed here. If this is not, but this is a non-homogeneous magnetic field, that is non-uniform that will be like this. The south pole is like this here. This is the south pole. Because the magnetic field, for example, if the magnetic poles are flat, so the magnetic lines will be like this. If this is north, this is south, so magnetic lines will be like this. So the magnetic field at every point in between these two poles will be same. That means this is a uniform magnetic field. So here the magnetic field is non-uniform because the poles are like this. So the magnetic lines will be bent like this, like this. So there is a change in magnetic field uh, by position, that is called as gradient of B. So here in this inhomogeneous field, the electron will experience a force. That force will be represented as F will be equal to gradient of magnetic moment associated with spin of the electron, that is mu dot of B. So it can be written as partial by partial x, because this is gradient, partial by partial x, partial by partial y, partial by partial z, that is along the three direction. But here the magnetic field is in particular direction, so it is in z direction, so we can represent the z component alone here. So we can write it as partial by partial z mu z dot b z, and z direction it can be represented as mu z partial by partial z b z, and z direction. So this is the given force experienced by an electron in this magnetic field due to spin. So here in front of this magnetic field there is a screen at some distance. So in this screen, so this is the expectation was the continuous silver atoms here, but this was not seen here. There are some these spots are discrete, not continuous. Fortunately, at the time of experiment, they was smoking bad cigarettes. That is, at this time, the cheapest cigarette was the sulfur cigarettes. So here, the sulfur atoms in presence of silver atoms in presence of sulfur, they react with sulfur and produce silver sulfide. So due to this presence of sulfur, there is the discreteness of the spots will be visible. Otherwise, it was not visible. Seen. So here the electrons will experience a force if these are supinous up. These supinous up will be deviated by the magnetic field and will be pointed here. Similarly, the supin downers will be deviated by the magnetic field and pointed towards this point. So this will be represented by supin up and the supin downs. So in this experiment, supin ups and supin downs or supin motion of the electrons was confirmed, and due to this supin, there is a magnetic moment associated with this supin motion of the electron. Therefore, we can write here, even if L is equal to 0, that is the orbital quantum number, orbital momentum, if it is 0, then also there is a magnetic moment associated with the spin of the electron. If we generalize the equation, that is the magnetic moment equation, mu will be written as Q, that is charge, general charge, divided by twice m into L. This is for orbital motion. Here it is a factor constant called G. G is called as Landigius factor. So this Landigius factor, its value is experimentally known for electron orbital motion, electron supermotion, nuclear supermotion also. So this can be written for electron orbital motion, G is here, this is orbital motion, we can write here GL. For supermotion, similarly, there is magnetic moment associated with it, that is mu. Here it is mu L, here it is mu S, will be equal to GS into Q upon twice M into L. This is associated with supin. So for electron, G will be equal to 1. So this equation becomes mu L due to electron orbiting will be equal to, here Q will be equal to minus E upon twice M into L. Similarly here, for supin motion, GS will be equal to 2, approximately equal to 2.002, that will be equal to 2, and here mu S will be equal to 2 upon 2, and 2 will cancel, that there remains minus E upon M into S. Here it is S. S is the supin angular momentum vector. So here you can write, so the total magnetic moment associated with the electron due to supin motion and due to the orbital motion will be the sum of magnetic moments. This, so the total magnetic moment can be written as so the net magnetic moment will be equal to mu is equal to mu L plus mu S, and will be equal to minus E upon twice M will be common, and there remains L plus twice S. So if L equal to 0, there is a supin magnetic moment. Mu due to supin will be represented by minus E upon M and S. This E upon M is called as gyromagnetic ratio. Here you see the mu will be written as minus E upon M. This S, that is the supin of the electron, is quantizer, so it can be written as Ms into H cross. Ms is, its value will be plus minus half. So we can write it as mu will be equal to minus E upon, due to this 2, that is twice M into H cross. H cross is related to H, Planck's constant, as H upon 2 pi. So we can write it as minus E H upon 4 pi M. This will be equal to, that is plus minus. So here it is plus minus, it is plus minus due to this plus minus mu B. This mu B will be equal to EH upon 4 pi M and is called as Bohr magnitude. Bohr magnitude. So this is the magnetic moments present within the material due to the orbital motion of an electron and due to the supin motion of an electron. Similarly, the supining of protons and neutrons within the nucleus will give rise to a magnetic momentus. Even though electron charge is here something, but the neutron has zero charge, but there is a supin motion. They are supining within about its own axis, so due to which the magnetic momentus will arise. So after this we can So in every material there are magnetic moments now, but they aren't in random direction. When we apply a magnetic field on a material, these magnetic moments will tend to align themselves in the direction of magnetic field for paramagnetic materials and for ferromagnetic materials. But in case of diamagnetic materials, they are oriented themselves opposite to the direction of magnetic field. So on the basis of one more parameter, these magnetic materials are classified into three categories, that is dia, para, and ferromagnetic materials. So in case of uh, these materials are classified on the basis of parameter that is called as chi. It is related to M and H as, that is magnetization induced in a material when placed in a magnetic field. Here H is the magnetic field intensity, so chi is called as magnetic susceptibility. Chi is magnetic susceptibility and is defined as magnetic moments induced per unit applied field. B. So therefore, on the basis of this chi, we can classify the materials like dia, para, and ferromagnetic materials. If its value chi is less than 1, then it will be negative. This is for diamagnetic material. Chi is, if it is greater than 1, then it will be positive. It will be positive for paramagnetic material. If it is very, very large, then it will be more positive for ferromagnetic materials, because the ferromagnetic materials are strongly attracted in external magnetic field. So the main contribution is due to the spinning of the electrons, because if we see in case of ferromagnetic materials are like iron, cobalt, nickel. So in these materials there are unpaired electrons present. Due to these unpaired electrons, there is a net magnetization present within the material, even if in the absence of magnetic field. So they are strongly attracted in magnetic field, and the value of the magnetic susceptibility will be very large, that is greater than 1. So this classification of magnetic materials will be discussed in lecture 2nd. So I hope you understand well. Thank you.